timing, good timing. Anything else you guys are trying to figure out? I think the answer is yes. Yeah. Yeah, I mean it's a matter of being able to grade it on time, and you guys can imagine the time that it's taking you to write it. Imagine what it's like to grade these things. It's so that's why. Did you guys have any kind of, I don't know, any other kinds of questions about anything? Did you see that I just posted over the weekend, I posted the next short homework. It's due on Friday, is that what I said? And it's basically computing a scarf complex, which is what we did last week. Did you have, I mean, really, we're about to switch topics completely, so it's a good time for questions if you have them. Okay. So, no questions? All good? So, we are going to switch gears starting today and for the rest of the semester, which is, I guess, 2 weeks left. And we're going to talk about lattice ideals. Okay? So, what's the point here? Well, the point is that we have spent almost the whole semester trying to understand monomial ideals. So you've seen that if we go back to where we started, we first developed some machinery of Grosvenor bases. And the point of that machinery, if you remember, was to kind of be able to take initial ideals, right? Because we wanted to analyze any ideal in a polynomial ring. And we kind of wanted to do that by reducing to the initial ideal, which is a monomial ideal. And so we spent the whole semester basically getting to that point where we develop Grosvenor bases that take any ideal to a monomial ideal. And then we spent the last about a month and a half talking about monomial ideals. This beautiful family of ideals, and we understand well how to compute their Hilbert series, how to compute their free resolutions, how to compute their Betti numbers, and we have all kinds of tools, right? We have the Hall complex, scarf complex, all these different machinery that we have developed, okay? But And this is something we should be proud of, right? I mean, it took hard work, but if you think about it, it's monomial ideals, right? And these are kind of the simplest possible ideals that you can think of. Right? And what we're going to do for the 2 weeks that remain is step a little bit out of the realm of monomial ideals and go to something more complicated. Now, I know that you realize, because you've done it in small examples, that if you want to do, for example, a free resolution for an arbitrary ideal, that's a complicated matter, it's messy, and it depends very much on what ideal you start with. And so what we're going to focus on next is kind of the next simplest family, which is the family of lattice ideals. Okay? So let me give you an example of what a lattice ideal looks like. Something like this. Okay. So this is not a monomial ideal. It's what's called a binomial ideal, because all the generators are binomial. Okay. And that's a general fact about lattice ideals. that they're all binomial ideals. So that is one sense in which these are kind of the next simplest family, because instead of having monomials where we have a single monomial, now the generators are going to have two monomials. But actually, even if you study binomial ideals in general, that's already a very hard question. And so we're going to focus on a specific family of binomial ideals, which is the family of lattice ideals. So every lattice ideal is binomial, but not every binomial ideal is a lattice ideal. By the way, since I just overheard some of you that you are encountering toric ideals in your project, I should tell you that toric ideals fit very nicely in this story, in the sense that every toric ideal is a lattice ideal, and not the other way around. But so somehow the point is that toric ideals are the nicest lattice ideals, and I'll show you that in a second, how that works. Okay, but that's what we're going to do next. And it's a bit of a challenge to figure out how to write things down today, because I'm going to make a bunch of definitions and I want to try to keep everything on the board. So first, we're going to talk about semigroup rings. Okay. So what's a semigroup? Semigroup is something that you may have seen before. One way of thinking about it is that it's something weaker than a group. So it's like a group, except that you have no idea whether you have an identity element, and you have no idea whether you have inverses. If you think about what that means all you have is a set, and you have an operation. Now, remember, what's a group? We have a set, a binary operation, and some conditions. So the conditions we have are that the operation should be associative, and we have that here. So the set is with a binary operation which is associative. But we don't necessarily have the other two conditions of a group, not necessarily have an identity or inverses. Okay? So a semigroup is something very simple. You have a set, you have a binary operation, and all you know is that this operation is associative. Okay? We are actually not going to care about general semigroups. We care about the following thing. We care about semigroups which are commutative. Okay. Have an identity and are finitely generated. Okay. So these are the kind of semigroups that we're going to see for the rest of the 2 weeks. And when I say semigroup, it's going to be implicit that I'm going to assume that it's commutative, that it has a zero, and that it's finitely generated. Okay? So how do I build such a thing? The way that I do it is that first I'm going to start with an abelian group. Okay? And I'm going to start with a bunch of elements in my abelian group. Okay. And this is going to define a semigroup of this sort, which I'm going to call Q, semigroup generated by these guys. And one way of thinking about it is that you basically, I mean, what can I do if I have these guys? Well, If it's generated by A1 up to AN, then of course those guys should live in Q. Now, this should be closed under the operation, and the operation is addition, right? So the only thing that I'm allowed to do is take all of these AIs and just add them up, right? And so what I get is just a set of combinations of A1 up to AN with natural coefficients, right? So this is maybe K1A1 up to KNAN, where these guys are natural numbers and these guys are elements of my abelian group. Okay? And I want to make this very concrete, so I'm going to have an example running through the whole class. What's your favorite abelian group? Do you have one? The integers. So that's already a good abelian group, and my favorite abelian group is a little bigger than that. It's the integer squared. Okay? And that's why I drew it over there. So we're going to start with just the abelian group z squared. So by the way, I hope you saw this. So today we have a seminar in this room from 3 to 4 p.m. It's Carola Mesaros from MIT, and she's going to be talking about something closely related to Juppé's thesis, which I think most of you were at. So if you like the pictures that she was drawing, it's the same. It's about triangulations of root polytopes. So I hope you go to that. So yeah, abelian groups. Remember that abelian groups are simple things, right? So generally, the abelian groups that we have in mind are either z to the n, or maybe z mod something, right? Z mod 5, z mod 8, and all the combinations of those, okay? So z squared is just this square grid, okay? And now I'm going to consider the semigroup generated by the points 3, 0, 1, 1, 0, 2. Okay? So let's draw that in here. Okay, so let's say this is the origin, and so my 3 generators are over here. So this is 3, 0. This is 1, 1, and this is 0, 2. Okay? So those guys are the generators of Q. And then what I'm going to do is just take non-negative integer combinations of them. Okay? So for example, I can take this generator and multiply it by 2 or by 3 or by whatever. So I'm going to get this point and this point and this point, etc. Okay? I can add the vector 1, 1, right? So that means that I can go from here to here. I can go from here to here. I can go from here to here, etc. Let's look at the next level. So for example, again, I can add a, so I want to fill this up from the bottom up, okay? So I can take this guy and add 1, 1, and I get this guy. I can take this guy, add a 1, 1, and get this guy, and this guy, so on. Now, is there anything else in the second row here? There is, right? So which one? Well, for example, this point lives in Q. Right? The point 3, 2 is the combination of this guy and this guy. So I get to put this one in. And in general, I can always take something in level 0 and add the vector 0, 2 to move me 2 levels up. So that means that because this guy is in Q, this guy is in Q, because this guy is in Q, this guy is in Q, etc. Okay? And I keep doing this. So this is kind of a fun game. I just, so I shift everything diagonally like this. Okay, so you start filling in this pattern. I can take anything in level 1 and move 2 up, but that's already in there, so I don't really get to add anything else. And so that's my level 3. Okay? I mean, this is already kind of an interesting question. So you can see that there's going to be some pattern emerging here. And I don't know what you might expect to see up here. Of course, here it's kind of sparse, and then it's getting thicker and thicker. What we'll see in this example is that actually all of this stuff is going to get filled up. Okay, so if we do the next level, you can move diagonally up like this, like this, like this. Okay, but I can also take anything in level 2 and move 2 up. So I get this guy, and I get this guy, and I get this guy, I get this guy, I get this guy, and I get almost the whole row. Okay, and then I get this. So hopefully you see the pattern of what emerges. Basically, I get everything up here, except here I'm going to get something like this. Okay. So this is basically it. From here on, I basically get the whole of Z2, except that there's these little holes here at every second level. Okay. And this thing that I drew here is Q. Okay, so that's an example of a semigroup of the kind that we're going to study. Does that make sense? Any questions about how I put this thing together? Okay. So now I'm going to define something which is called a semigroup ring. So the semigroup ring of Q is the following thing. So the elements are just going to be things that look like this. What we're going to do is that we're going to take each one of these things in Q and think of it as t to the something. This is something that we've seen several times. Okay. Well, let me write down the definition, and then I'll say a couple of words about it. So what I do is that I take linear combinations of things that look like t to the bi. Okay, where the idea is that lambda I should be in my field, my favorite field. And so that field could be anything, right? It could be the complex numbers, it could be the reals, whichever one. And then these BIs should be vectors in elements of Q. Okay? So, for example, what do we get in this case? Well, what I get to do is, I mean, what's an example of an element that lives here? Well, I take some elements of Q. For example, I don't know, 3, 0 is in Q. 3, 2 is in Q. And maybe, I don't know, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So for example, these are 3 elements of Q. Okay? And so I can make an element of f of Q by just taking any combination of these guys, except that we do the thing that we've done several times in this class, where what you do is that you take some constant times t to this thing, right? Plus some other constant times t to the 3, 2, plus some other constant times t to the 6, 5. Okay? And as we have done before, this means you take, I mean, you're raising a vector to a vector, right? So what this means is t1 cubed t2 to the 0. This is t1 cubed t2 squared. This is t1 to the 6th, t2 to the 5th. Okay? And so I'm just going to write this as the linear combinations of things of this form, t to the a, where a is in Q. Okay. And if I want to say more explicitly what this is, well, what does a linear combination of these guys look like? Well, it looks like, let's say, x times 3, 0, plus y times 1, 1, plus z times 0, 2, right? So if x, y, and z are natural numbers, then this is an element of Q. And every element of Q is of this form, right? So when I figure out what this is just, what, 3x plus y, comma, y plus 2z. And so if I want to say very explicitly what lives here, well, they're the linear combinations of these things. Okay. Now, if you see what I defined for you here, I defined the semigroup ring, and I'm saying it's a ring. Right? Now, so far I told you what the elements of this ring are. They're things of this form. But now we need to talk about how to make this into a ring, right? So if you want a ring, you need to know how to add elements of this form, and you need to know how to multiply elements of this form. And maybe it's just clearest if I do this in an example. So let me take two elements that live here, like okay. So this is an element of my semigroup ring. And another element might look like this. Okay. So then, of course, how do you define the sum? Well, it's just the sum, right? I mean, you take this, and you take this, and the answer is this, right? So I'm not telling you anything too interesting there. So it's kind of clear how to define the sum over here, which makes sense because here I'm telling you this as a vector space, linear combinations of F. What is a little bit more interesting is how do you multiply here? Okay? I need to give you a rule that tells you if I want to multiply this element of f of q times this element of f of q, how are you supposed to do it? And I don't know. What would you do if I forced you to multiply these things? I'll take suggestions. You kind of do what, I mean, sometimes ignorance is bliss, right? You just do what probably works, and you hope that makes sense, right? So you distribute, right? And so you say, okay, well, I don't know how I'm supposed to multiply here, but I would distribute, right? That's what I would do. So I would say, let me multiply this times this. And the way that I would do that is probably that I would multiply the scalars, and then how do you multiply t to the 3, 0 and t to the 6, 5? You probably want to add up the exponents. So you get this plus, and then you multiply these two, you get bc times t to the 9, 7. Okay? And that's exactly what you do. That's how this product is defined. And one thing that we need to talk about is why is it that the result lives in Q? And what's important is to notice that if 3, 0 was one of the exponents that appeared here. Sorry, I need to justify why this lives in f of q, right? If I multiply two things in f of q, I should get something in f of q. And this is going to live in f of q if the exponents live in q. Right? because f of q consists of things whose exponents are in q. So why does 9, 5 live in q? Well, because 3, 0 lived in q, 6, 5 lived in q, and in a semigroup, you do know how to add things, right? So if you take this in q and this in q and you add, you're supposed to get something in q. So that's why you get this. Okay. So the semigroup is just this thing with multiplication given by t to the a times t to the b equals t to the a plus b. Okay. So maybe there's a couple of comments that I should make here. So generators for this thing, for the semigroup ring. Okay. What can I use to generate my semigroup ring? Well, there might be a couple of different answers to this. So for example, as a vector space, what does it mean to generate as a vector space? It means you want to choose some elements in here such that every element of f of q is a linear combination of them. Okay? And so just by the very definition of this, the natural basis of f of q is this, right? T to the a, where a lives in q. Right? By definition, everything is a linear combination of those. But if you want generators as a ring, then you have a little bit more freedom, right? Because, for example, I wanted to get t to the 9, 5. If I want to get it, well, I can actually get it as a product of smaller things, right? And so actually, as a ring, it's enough to just take t to the a1 up to t to the an, right? And then you can multiply all of those guys together to get t to the a for any a in q. And that's how you can get every element of your semigroup ring. Okay? So if you're interested in generating as a vector space, you need this very large set of generators. If you're interested in generating as a ring, where you're allowed to multiply them, then you just need the n guys that you started with. So what I'm saying concretely in this example is that if you want the basis of this thing as a vector space, then you need a generator for every black dot, right? And an element of the semigroup ring is 5 times this black dot plus 8 times this one plus 9 times this one. So that's a vector space basis. But as a ring, you only need these 3 blue generators, right? And if you want to get any black dot, you can get it by multiplying some of the blue guys. Okay? So that's how we get this thing. Okay, so I need to make another definition. So first let's define, so consider this abelian group homomorphism. So I'm going to consider a homomorphism from Zn into A. And what this homomorphism is going to do is that I'm going to take each one of the basis vectors here, which is indexed by E sub I, and I'm going to send it to the corresponding element AI of A. Okay? So this is a group homomorphism because I just define it on the basis and I extend by linearity. So let's see how this looks in a picture. So in the example that we have here, n is equal to 3, right? And so what we have is a homomorphism from z cubed into the lattice A. Okay? So let me draw it like this. And then I'm taking the basis vectors. Okay, so I don't know. Maybe this is the x-axis, the y-axis, and the z-axis. Okay, and I take the basis vectors. Maybe they're here, and here, and here. Okay, this is a three-dimensional picture, right? So it's z3. These are the three basis vectors: e1, e2, and e3. And I'm saying consider the map phi that takes z3 to A, which is this guy over here. And what that map does is that it takes e1 to a1, e2 to a2, and e3 to a3. Okay. And then every integer point over here in Z3 is going to map to one of the integer points over here. Okay? So if you look at this, I tried to draw it suggestively so that you can just see this map over here as just kind of looking at the picture and forgetting that it's three-dimensional. So really, this is a three-dimensional picture, but if we look at the way that it's drawn on the board, that's a homomorphism. Okay? And I tried to line it up so that these guys have the same shape as these guys. I think I failed, didn't I? I think E2 should be down here. Okay, but so that's a homomorphism. Just forget that this is a three-dimensional picture. Okay? And what I'm going to do is consider the kernel of that homomorphism, which I'm going to call L. Okay. So what is L in this picture? Well, it's basically precisely the points that we are not seeing by seeing that this is a three-dimensional picture. So there's kind of a line here, which, you know, if I drew it correctly, then the line just looks like a point, because it's exactly where my view is coming from, right? But it's really a line. Okay. So let me just move it out a little bit so it looks like a line. Okay. But this is precisely. These are the points that map to the origin here, okay? But we're looking at Z3, right? This is not R3. And so this is actually a line consisting of just a bunch of points. Okay? Right? And these are the points that get mapped to 0. So this is a lattice. Yeah, sure. So, I mean, one way to see it is this, that here you have something three-dimensional, and here you have something two-dimensional, right? And if the image of this map is two-dimensional, that means that the kernel must be one-dimensional. So there must be some line that you're losing by going from 3 dimensions into 2 dimensions. Okay? Now, if really my picture was accurate, and the map phi was just taking this 3-dimensional picture and just ignoring or realizing that you cannot really see in 3 dimensions, right? By the fact that I drew this picture in the plane, there actually is a line sticking out of this point that you're not seeing. And those are exactly the points that look like 0. Okay, so it's this line that I can't really draw on the board. That's the kernel. Okay? And I'm just tilting it over a little bit so that I can draw something. But really, the way that I should draw it would just be as that point, which is kind of sticking out of the board.
So would those be like all linear combinations?
Exactly. So I actually wanted to carry out that computation. So L consists of basically the x, y, and z such that the x, y, and z cubed such that this linear combination is 0. Yep. I'm sorry?
So where does negative E3 go?
Oh, so I mean, the thing is that Q is the black dots, but A actually extends over here also. Right? A is the whole lattice, is the whole Z2. A is Z2, so really it keeps going over there. And Q is these points that I drew. So for example, the negative of E1 is going to go to the negative of A1. Okay. So we can say very explicitly, I mean, of course, this is a line, right? Because it lives in 3 space and it has 2 equations. It's a line. And if you just look carefully at what the solutions to this thing are, they're just the multiples of the vector 2, comma, minus 6, comma, 3. You just solve it, okay? And you find that y should be equal to negative 3x, y should be equal to negative 2z, and everything should be an integer, so that means that this is the smallest solution and everything is a multiple of it. So this point right here is 2, comma, minus 6, comma, 3. Okay? And that's a lattice, and by a lattice I just mean a subgroup of the line or whatever Zn you're living in. Okay, and then, so is the definition of L clear now? So finally, I think this is the last definition. I need to tell you what the lattice ideal is. Okay? And the word lattice comes from the fact that this is a lattice. By the way, so you know that we have 2 meanings of lattice in mathematics that don't have anything to do with each other. So if you don't know that and you only know one notion, then you know the right notion, which is a lattice, right? Like the points on a square grid. And there's also a notion of lattice in combinatorics and posets that has nothing to do with this. So if you happen to know that, then forget that. And I'm talking about this lattice, like the kind of grid that you're used to calling a lattice. Okay? By definition, a lattice is a discrete subgroup of Rn, and what that means is that it's a grid. Okay, so then I define the lattice ideal. I sub L is the following thing. It consists of, it is generated by things of the form x to the u minus x to the v, where u minus v is in the lattice. Well, so u and v are non-negative vectors, and their difference is in the lattice. Okay? So for example, what does that mean here? It's generated by here's one of the generators. X squared z cubed minus y to the 6th. Why does this live here? Well, because the vector here is 2, 0, 3. The vector here is 0, 6, 0. And those are both non-negative vectors, such that when I subtract them, I land in my lattice. So this is one of the generators that you get. Can you tell me a different generator? You have a lot of freedom. All you have to do is choose some non-negative vector, some other non-negative vector, and have their difference be a multiple of this thing. I welcome your suggestions. So maybe what I'll ask you to do is give me two non-negative vectors whose difference is in the lattice. And so it's something like this: x to the fourth, y to the fourth, z to the fourth, minus x squared, y to the 10th, z to the 1. Good, so that's another thing that gets to live here. Now if you look at this, that was a lot of work, and it was not really worth it to do all that work, because this is a multiple of this. Yeah? And it turns out that actually everything is generated by this thing in this case. So a priori, you have to do this for every u and v. A posteriori, it turns out that you get a nice finite list, and in this case, it's just this. That relates to, well, we'll see what that relates to. I mean, that's one of the questions that we're after. How do you choose nice generators for I sub m? So that's how this goes. Okay. And so this is the setup, and I realize there's a lot of definitions, and that's why I wanted to be very organized and have everything on the board. So it's a lot, but it fits all together in two boards: the left board and the left board is the definitions, the right board is the example. Okay. Maybe what we should do next is do a different example. I don't know. Do you want an example or a theorem? Example. Okay, I agree. I want an example too. I want to show you how you can get this guy. Okay. Because of course, so what am I saying here? I'm saying this is a lattice ideal, but you realize that's kind of a hard thing to verify, right? So you have to find the A and the Q that'll give you this. You can't just spot it and see, oh, that's a lattice ideal. So I prepared class, and that's why I know it's a lattice ideal. So let me give you the A and the Q. So this is example 1. And let's do example 2. A different abelian group. In fact, let's choose the smallest abelian group, Z2.
Well, that's a trivial one, yes.
So it's debatable. Actually, some people define a group as the... Anyway, let's not choose the trivial group because that's too trivial, but let's choose the smallest thing, which is just Z2. The smallest non-trivial abelian group. Okay, so this thing really has two elements, 0 and 1. And let's choose, we need to choose A1 up to AN. Okay? And this might be a little funny, but I'm actually going to choose 3 elements here. But you realize I don't have much freedom, I don't have much room, so I'm just going to repeat elements. So A1 is 1, A2 is 1, A3 is 1. Okay? Can't stop me. Can't stop me from doing that, so I'm going to do it. So then what? What's the semigroup ring? Well, so let's draw this very interesting picture of A. Here's A. And what's Q? It's only 4 possible answers, right? Because it has to be a subset of A. So what's Q? Well, Q means taking natural combinations of these guys. So you're allowed to take these guys, and you're allowed to add them up. And so that means that you can get 1, and you can get 1 plus 1. So Q is equal to A. So what's f of q? Well, f of q is generated as a vector space by t to the 0 and t to the 1. So what are its elements? The elements just look like a times t to the 0 plus b times t to the 1, where a and b are in my field. Now, you should realize that this is a little bit strange, right? I'm raising t to the 1 bar, where 1 bar is some element of this. So, I mean, this is really not an integer, right? So I'm just kind of saying, well, I define the semigroup ring to be like this, and so the elements just look like linear combinations of this, and I think we should spare ourselves the philosophical debate as to what this actually means. It's just some symbol, t to the group element. And I know how to multiply t to the 1 times t to the 1. It's t to the 1 plus 1, which is t to the 0. So that's all. I don't want you to think that this is some other meaningful thing. It's just that. Okay, so that's the semigroup ring. Now, what about the lattice? So the lattice is what? Well, we need the points in Z3 such that the combination x times 1 bar plus y times 1 bar plus z times 1 bar is equal to 0 bar. Yeah? Just the same as here. So which points x, y, z satisfy this? Well, this is just x plus y plus z mod 2, right? And so what we're going to have is that this is the lattice of x, y, z, and z cubed, such that x plus y plus z is even. Okay. So what about I sub L then? I sub L is going to be generated by things of the form x to the u minus x to the v. But here I have 3 variables, so let me just write those out. Okay. So this is just x to the a, y to the b, z to the c, minus x to the d, y to the e, z to the f, such that a, b, c minus d, e, f is in my lattice. Okay. But if you think about it, actually that's kind of an easy condition to check. If I want to know whether A, B, C, D. I mean, if I need to check this condition, all I should do is just add up those numbers and make sure I get an even number. Right? So I need A plus B plus etc. up to F is even. And I do need them to be non-negative. Okay? And so those are the generators for my lattice ideal. And now we can just start putting exponents. Okay? So you have the freedom, and actually I want each one of you to think of a generator. So what are you supposed to do? All you need to do is just choose numbers A, B, C, D, E, F. They should be non-negative integers, and their sum should be even. So I want each one of you to think of a generator here. Okay. Do you have one already, Ray? Anybody? Y cubed minus x squared y z to the fourth. How do we know if Amanda is right? The only thing we need to do is add up the numbers 3, 2, 1, 4. That's a 10. That's even. So it goes. That's of that form. Okay. So give me a smaller one. All zeros? All zeros is 1 minus 1. I guess that counts.
Too small, eh?
A little bit too small, but it's true. 0, 0, 0, 0, 0, 0. They're all non-negative, and the sum is even. X squared minus 1, right? And now you see where that x squared minus 1 is coming from. And if I have x squared minus 1, I might as well put y squared minus 1, z squared minus 1. Anything else? X minus y. And if I have x minus y, I might as well have y minus z and x minus z. Anything else? I wrote xy minus 1 earlier, right? And if I put xy minus 1, I might as well put yz minus 1 and xz minus 1. Okay? And each one of you should put in your notes the one that you chose here. I don't know. I chose y to the 100, z to the 314, minus x to the 12, y to 7, z to the 11. So like I said, a priori, infinitely many generators. But then if you look at this a little bit more carefully, you'll see that actually this thing is generated by what I said. X squared minus 1, xy minus 1, xz minus 1. Okay? So we all agree that these